Before we can proceed in our quest to find digits of pi, we must make a quick detour to discuss Euler's identity. You may have seen this before. Some people say it is the most beautiful expression in mathematics because it involves 5 of the most ubiquitous constants, e, I, pi, 0, and 1. All of them are combined together in such a simple expression. What we can use to prove that is the more general expression, e to the I theta is equal to cosine theta plus I sine theta. This is often referred to as Euler's formula. Plug in theta equal to pi and see what happens. Cosine of pi radians is equal to -1. Sine of pi radians is equal to 0. Thus, e to the I pi is equal to -1. If I add 1 to both sides, I get the expression boxed in orange. Euler's identity. While what follows is not a rigorous proof, it does give a very intuitively satisfying explanation as to why Euler's formula is valid. To begin, we must use the Taylor polynomials for the exponential, sine, and cosine functions. Here I have provided a convenient reminder of what those are. Any worthwhile standard calculus textbook will include a more detailed explanation on the Taylor series. Furthermore, I have touched this topic in other lessons as well. What happens if we plug ix into the Taylor polynomial for the exponential function? Well, that's what I've done in the first line. The second line I have distributed the power to both I and x in each term. Boxed below that is a reminder of our rules for imaginary numbers. Specifically, the imaginary number to a power is shown for I squared, I cubed, and I to the 4th. This pattern repeats for I to the 5th, 6th, 7th, 8th, and so on. Using those simplifications, we can collect like terms. By separating out the real and imaginary, we have 2 polynomials in parentheses. These look awfully similar to cosine and sine. Indeed, that's exactly what they are. Thus we have shown that e to the ix is equal to cosine x plus I sine x, Euler's formula. You may be wondering why I brought this up. Don't worry, it all ties into the master plan. Remember that any complex number can be represented as a vector in the complex plane. This is a simple pictorial representation of that. By definition, a is equal to r cosine theta and b equals r sine theta. Using the Pythagorean identity and simplifying, it can be shown that r is equal to the square root of a squared plus b squared. Taking the ratio of r sine theta over r cosine theta, we find that theta is equal to inverse tangent of b over a. This was also obvious from looking at the image on the previous slide. Here is some real utility of Euler's formula. We can multiply 2 complex numbers by foiling them out and collecting like terms. That's what we've done in the past, and it can be cumbersome. However, we can also rewrite them as vectors using r and theta instead of a and b. That's where Euler helps us out. The product of 2 exponentials can be rewritten as e to the theta 1 plus theta 2. This all comes back to high school algebra rules. Even more helpful is when we raise a complex number to a high power. Instead of foiling a bunch of times, we can use Euler's formula to greatly simplify the process. I've included step-by-step details for you to follow along. Again, it all comes back to exponential rules from high school algebra. This is going to make the process much easier. Stay tuned for the next lesson, in which we will implement this slick shortcut. Thanks for watching. I will see you then.